Okay, welcome back to Deep Learning Systems Algorithm Implementation. I'm DQ. So today we're going to learn about how do we use different techniques to train large models. And the lecture is going to be divided into two parts. In the first part, we're going to talk about what are the common techniques we can use to build deeper neural networks and fit them onto limited memories that we have on modern GPUs accelerators. In the second part, we're going to talk about some of the common paradigms we use for parallel and distributed training. Okay, so to begin with the first part, and let's come back to why we want to talk about learning large models. In a lot of cases, when we start to think about building machine learning and machine learning applications, there are a lot of things that come into play nowadays. Of course, we want to be able to build ever increasingly flexible models, and those models will need to learn from a bigger data set in a lot of cases. And in order to learn from bigger data set, we will need to be able to build those models using the advanced compute devices we have. A lot of cases they will involve GPU that you learn, as well as some of the acceleration devices. So in order to do that, there's really a question about how do we scale up this learning process, right? Can we fit bigger models onto limited device we have, as well as how can we just scale up the training process so we can go and leverage more devices available in there. So these are the two questions we're going to study in today's lecture. As the first part, let's start to talk about the GPU memory hierarchy, since we just learned about GPU programming. And remember that in terms of GPU hierarchy, of course, we have like the stream multiprocessors. Within stream multiprocessor, we have limited shared memory, 64 kilobytes in here. But besides those things, when you go and buy a GPU, like say, I'm gonna go and buy 3080, right? There is a tag that covers GPU on how much GPU memory that you have, and this is usually refers to a global memory that you have on GPUs. And depending on the device, the global memory size can be very different. For example, a common commercial card that you can get will give you around 10 gigabytes or sometimes 8 gigabytes of memory. And the modern GPU like 800 will give you much bigger memory size, right? Like 40 gigabytes, 80 gigabytes in total. So this is like an overall GPU memory that we have. And in all cases, when we say, we want to be able to train a big neural network, right? A lot of the modern applications are bottlenecked by the global memory size we have. For example, when I worked on, when I was a PhD student, that's usually a saying of, the biggest neural network that you can train on ImageNet is, ResNet 200. This is because most of the GPU there only have 8 gigabytes of memory. And ResNet 200 is kind of the biggest size you can fit into this 8 gigabytes memory without some of the smart tricks that you have. So that's certainly like one important factor to consider in terms of, can we fit as big of neural network training onto the limited memory devices? Of course, you can find a common trend is that some of the server class card like 800 start to increase the amount of GPU RAM exactly because of the reason, because as we start to build bigger models, a lot of models will also cost bigger amount of memory size in total. And those bigger amount of memory size will come back in turn, put the kind of demands on the GPU memory that we have. And as a result, most of the server cards start to increase the size of the GPU RAM available. Okay. But one question we all ask, even with the consumer card, right? If we have a like RTX 3080, will we still be able to train those bigger models that is out there? The answer is yes. We will. There are like tricks that we can use to reduce the overall GPU memory consumption on learning those bigger models. So let's start to think about, before we start to dive into the methods, let's start first think about what are the common source of memory consumption that we can have. I'm going to use a simplified view of computational graph training, so you can find that here is effectively the forward parse. that takes in your input and apply different stage of operations, and finally gives you a loss function. And here is a gradient path, right, that takes in your label and incrementally apply some of operations and then effectively gives your input. And there are multiple sources of memory consumptions in here. First of all, of course, we want to be able to store, in a training case, we want to be store the weights as well as auxiliary optimizer states like, the momentum variable and so on in here. Another thing that is a common source of memory cost is the intermediate memory activation values. So for example, when we take the input, we apply it to linear, then I need to be able to use memory to store the results of a linear activation. Right? So there's always this intermediate activation values that you need to use in here. And of course, there are other sources of memory consumption as well, besides the model weights, optimizer states, and intermediate values. For example, we will need to be able to allocate data, right, to be able to store the input data and so on. So these are like a common sources of memory consumptions. Now, one question that we have is, how can we reduce the overall memory cost in this process? If you look at this computational graph, you can find that at least, every node kind of costs memory. So what are the possible techniques we can use to reduce that? I'm going to pause a bit. Everybody think. Then I'm going to also come back to the next slide so that maybe we'll get a better sense on, what I mean in terms of possible ways of memory saving. So let's start with a simpler case. In this case, let's assume that we only consider the problem of inference. So in the case of inference, the idea is that you're going to take your input data, right? You are going to apply different step or transformations. And then we are going to effectively only care about the final output or loss function here. Then the question here is how much activation memory that we need to spend in order to run this inference job. Assume that we have a very deep neural network that contains n layer, where n can be, say, 1,000. So one interesting thing here is that, as a matter of fact, of course, we still need to be able to store the weights of each of a linear layer here. So that piece, the weight still increases with the number of layers you have. But in terms of the cost of storing the activation memory, for this like n-layer neural network, as a matter of fact, you only need 2 buffers or two pieces of memory buffers to be able to run this inference. To see why it's the case, you can see that I can use, say, buffer A to store the result of a linear layer. And then I'm going to use buffer B to store the result of a ReLU layer. But then as I start to compute the result of next linear layer, we know that buffer A is no longer being needed because we already get the value of ReLU B. So I can use A again, B again here. So the effective idea is that we can cycle through 2 buffers in a ping-pong way, right? So you start with 1 buffer, you store intermediate results there, you run some of the computations, you store the output to the next one, you cycle in an alternative fashion. And in this way, you can find that no matter how deep my neural network is, we just need 2 pieces of like a scratch pad memory in order to run this feed-forward inference. Of course, real-world models are much more complicated than this one. So in this case, there will be different kinds of memory sources of memory consumptions. Like for example, if I have skip connections, you cannot immediately deallocate the buffer A, right? So, but there are possible techniques that help us to be able to reduce the memory as much as possible. And in other cases, because the dependencies are really local, right? So as the neural network grows deeper, likely we are only still going to have a constant piece of memory for storing activation. Of course, we still need to spend amount of memory to store the weights, right? So that is something that's not negligible in this particular part. Okay, so these are the common techniques for saving for memory saving in terms of inference. And a lot of these techniques are being used so that we can afford to run very efficient inference on small embedded devices that only contain really limited size. But then comes another kind of perspective. If you start to think about training, which is a lot of cases what we care about, and then things becoming more complicated. So if you look at this particular computational graph, it is a simplified view. So you can find that in reality, there should be weight 0, and there should be things like weight and weight being attached to here. And when we're doing, the gradient values, we will also need to be able to, it's also going to depend on the weight here, right? So the weight is being omitted for simplicity. And you can find that here's the forward pass that takes your input and tries to be able to compute the output. Let's ask the same question. If you want to increase the number of layers in this neural network, you'll find that effectively we cannot use this, no longer use this ping-pong buffer approach. Why is the case? If we use like A, B, and A in this case, you'll find that, well, in this case, the result of this value is being overwritten by the result in here. But after we do gradient computations, I still, in order to compute the result, I still need the result of A right here. So effectively, you can find that in the gradient calculations, there are these dependencies that depends on the values in the forward computation. So in order to be able to compute the overall gradient computations, there's always those ladder values in there. You can view like this gradient computation like a ladder, right? Always this ladder values that depends on the forward computation. As a result, we can no longer immediately deallocate or reuse the values in the previous stages of computation. So in general, if we go and directly leverage this automatic differentiation algorithm that contains those ladder dependencies, then in order to train an n-layer neural network, we will need to be able to allocate O of n, right? So the number of activation intermediate storage is going to be dependent on the number of layers in here. And that is why when we are doing, training of deep neural networks, it costs much more memory than inference, because in a lot of cases, because of the dependencies from the forward value, we can no longer use the simple approach of, doing ping-pong recycling or do a lot of memory smart reuse. Okay, so I'm going to pause a bit and then let's start to ask the question. What kind of possible approaches can we use to reduce the overall activation memory cost for training? Of course, it's no longer going to be as simple as, just go ahead and reuse it, right? So, excuse me. So, what is the possible technique here? And one interesting fact is that, yes, there is a way to go ahead and reduce overall memory consumption here. And so I'm going to, in order to simplify the introductions moving forward, I'm going to use an even more simplified view to try to combine the gradient and forward computation. So in this case, I'm going to use this to indicate the forward computation. I'm going to directly use this backward arrow to indicate this, gradient computation path in here. So this figure is a bit more like a forward and backward propagation, right? But in reality, that's still going to remember that under the hood, there's always this, gradient computation path that corresponds to the backward path in here. Okay, so in reality, we can still leverage the computational graph computation engine under the hood. Okay, so let's start to introduce the technique that can help us to reduce the overall memory consumption in specifically the activation memory consumption in training process. So this is a technique called activation track pointing, or uh, gradient or track pointing in this case. Okay. So in order to do that, as a first step, we're still going to do the forward computation, right? So this is doing the forward computation in here. But one of the things I want to note in here is that there are those colored nodes. In this case, when we're doing the forward computations, we are going to, of course, remember the values of those computed results on those colored boxes. In the meantime, there are also this white, there's also this empty boxes in here, right? In this case, the empty boxes means that as soon as I compute a result and I compute next value that depends on the result, I'm going to deallocate the memory on those empty boxes. So effectively, after we finish the forward computation, we're only going to store the values of the colored boxes here, and of course I'm going to get my output here, right? So in this computation process, I'm going to get my output value, and I'm going to store the result of those colored nodes, and these are what we call a track point that going to remember the values of these corresponding stages. Okay. Now we want to compute the gradient value, right? And we want to be able to compute a gradient with respect to each of a weight. How can we do that? Let us assume that for now I don't care about computing gradient of all those first few layers, and I only care about gradient values of the last 3 layers here. Okay. What can I do? Of course, I want to be able to compute a gradient with respect to this layer, right? And however, in order to do that, in order to propagate my gradient values from here to here, likely I will need to know the value of this box. However, this box is empty now, so that means that I no longer know the value in here because it's being deallocated. So what can we do? The idea is very simple. We're going to go ahead and recompute this value. So in this case, what I'm going to do is I'm going to run this another tiny forward computation that's going to fill in the value of the empty box. Okay. And after we run this forward computation, now we know the value in here, right? Because we run this forward computation in here. And then I will be able to run the gradient computations, and I will be able to calculate adjoint here and adjoint value in here, right? So up until now, we will be able to get the adjoint value of each of the layers if they have weights on them. We'll also be able to get the adjoint value of this particular node in here, right? So not only will we be able to get adjoint value of the final loss function, we'll be able to get adjoint value of that particular node through this tiny gradient computation step. Of course, in order to compute the overall weight updates, we also need to be able to compute adjoint value of a weight in here, right? And adjoint value of this weight. How can we do that? We can run the same gradient computation again. Remember that now we already have adjoint value up until this node, right? So the only thing we need to do is to try to propagate this adjoint value further back using the reverse mode automatic differentiation averaging. And same thing happens in here. We cannot directly do the computation because I don't know the value of this empty box in here. So what do? We will run the same forward computation again to fill in those empty box, and then we run the gradient computation. That will give me the adjoint value of each of the layers. Okay. So to summarize, you can find that in step 0, the goal is we only checkpoint those colored nodes and trying to delete the value of those empty boxes. And within each of a small step, what we do is we will try to recompute the value of empty boxes, and then run the gradient computation, and then run the recomputation and gradient computation again in here. We're going to pause a bit and let's start to think, why it can save memory in this case. it seems that it looks quite similar to the computation we have. Why I can save memory? So one thing that we might want to note is that, first of all, in the forward computation, of course, it costs you less memory because we only remember the color node here. So you don't have to, allocate memories for those empty boxes. Of course, we are going to save memory in the forward computation part. Then there's also a question about then there's a gradient computation here, right? That runs this mini forward and backward. One of the things I want to notice is that, of course, we're going to spend memories on running this mini segment because I will need to allocate more memory, right, to be able to fill in the blanks of this deleted node. As soon as I finish this gradient computation and get edge on here, I can go ahead and delete activation memories of the other nodes because they are no longer being needed. In order to compute this mini segment, I just need to know the edge on value of that particular node. What does that mean? That means that throughout this entire process, we're only going to spend one piece of memory to compute a small segment, right? And we don't have to spend the memory to compute all the segments. And that is where we can save memory. Okay. We can also go ahead and try to run a careful calculations of what are the things being involved in here. So in this case, if we run a forward computation and let's say we checkpoint every k layers, that means that in total that's going to be n divided by k checkpoints. And we need to remember n divided by k color nodes effectively here. Okay. Of course, because of the length of the segment is k, right? In order to do recomputation, we will need to have O of k over all memory cost in here. Okay. So if you look at this formula, if we go ahead and pick k equals square root of n, one amazing thing here is you can find that my overall memory cost is O of square root of n. What does that mean? That means that if we are going to do a training of n-layer neural network and we're going to apply this particular memory saving technique, you are going to get a sublinear memory cost with respect to the total number of layers that you have. Isn't that amazing? That means that you will be able to fit a much bigger neural network onto the limited GPU memory that you have in here. And of course, depends on the actual computation graph. You don't necessarily have to do like a checkpoint every k layers. So, and another thing that I want everybody to start to think about is what are the additional, of course, we are doing recomputation. So we are spending a bit more computation than the simple gradient calculations that don't do that recomputation here. What are the additional computational costs we're spending here? You go ahead and look. You find that if you're just going to do the forward and gradient calculations, right? That's the common way of doing it. But in this case, by doing one forward, one of a mini forward, one mini backward, one mini forward, one mini backward, you can find in total, actually, we just spend one additional cost of running a same forward computation, okay? So normally in practice, the cost of the forward computation is about half of the gradient computations normally. As a result, you can find that, effectively we are going to spend a bit about 25% of additional computation cost compared to the original vanilla averages. So effectively, we're not spending that much. You're just going to spend 20%, 25% more time. It buys you a lot of memory. So this sublinear memory cost saving algorithm is being widely used. So if you go and train deeper models, you want to fit a very deep model onto your limited GPU memory, likely this is the algorithm that you're going to use to reduce the memory cost. Of course, we don't necessarily have to do the, we don't necessarily have to pick k equals square root of n. So there are other ways that we can pick. For example, in our cases, we know that the cost of recomputing different layers are different. For example, if you want to go ahead and recompute a convolution or matrix multiplication layer, it's going to be much more costly than recomputing the result of ReLU or other cases, right? So you could choose to, for example, only recompute those cheap layers as opposed to those, more heavily computational heavy layers. In those cases, likely you wouldn't be able to get a square root of 1 sublinear memory saving, but still going to be a very significant amount of memory saving that you're going to get in this overall process. So that's also there are also a lot of follow-up works on how you can effectively use such kind of gradient checkpointing, or another way they call it rematerialization technique, to be able to get a more memory efficient training process. Okay. So we've talked about the techniques for memory saving. Let's switch gear a bit and start to talk about techniques of using parallelization and distributed training. Of course, in order to be able to train a very big model, in a lot of cases, we might get a case where your single model do not fit into a single GPU. So we want to be able to, or you just want to get a bit more acceleration to be able to get all the models, to get more GPU computing power to accelerate our overall training process. And the question here is, how can we go ahead and leverage possibly multiple devices that are distributed over several worker nodes to be able to train a model end-to-end? And there are different ways for us to do this overall model training process. One of the ways to do model training is we're going to map different part of the computations onto different workers. In this case, each worker can correspond to a single GPU, for example. So that's the common way to do things. And in this case, this is a particular model that corresponds to what we call a recurrent neural network, where you can have like a sequence length dimension and a depth dimension here. And we can try to map each parallel computation here. One interesting thing about this computation is you can find that as soon as I start to finish this particular computations, I will be able to run this follow-up computation immediately. So you can find that actually my parallelization happens in this wavefront fashion in here. Of course, in model parallel training, it's not always possible, but it is like, if you have such kind of opportunities, you should be able to go ahead and leverage it. So in general, if I have a computational graph and I want to be able to break it up for getting model parallelism, a general approach is that you're going to take this computational graph and you're trying to partition it across different workers, right? So you will be able to get that this worker is going to work on this part, this worker is going to work on this part, and so on. And once you get this, what you're going to do is you're going to go ahead and partition them. So in this case, I'm going to break it apart. And then we're going to play what we call send receive pairs in the boundaries of a computational graph. So in this case, we are going to, the worker 0 is going to take data, do the forward computation, and this point is going to send the result onto the worker 1. Then worker 1 is going to receive the data, gradient computation, send the result back, and then it's going to get to the final gradient computation here. So the effective way to break up a computational graph is just you go ahead and you take your computations and you try to break it apart across different workers, and you insert this send and receive pairs. The one thing that you might notice about this computation is that there's not a lot of parallelism in here. So in practice, what people normally do is they will apply a technique called pipeline parallelism. So the idea is that we're going to go ahead and run computations. So we're going to go ahead and run a computation of the first, what they call micro batch. And then, of course, worker 0 is going to take over and run the second part of computation. Right? But as soon as it starts to run while the worker 1 is run the second micro batch, it's going to go ahead and run worker 0 is going to run another micro batch in here. So effectively, the computation of the first micro batch on worker 1 in here is going to be run concurrently with this one. Okay. So similarly, right? So you will get so in this case, actually, we will be able to get, this is going to run on a second timestamp in here, right? And then while this is going to run on second timestamp, actually, we also will be able to get this. It's going to run second timestamp concurrently in here, and then that's going to have a third micro batch going to come out in the second timestamp. So the idea is that we're going to have this pipeline parallelism going on, so that while another worker is working on while later worker is going to work on a previous micro batch, the previous worker is going to go ahead and start work on next micro batches to keep this pipeline busy. In general, if we're going to have a lot of micro batches, then we are going to be able to get enough amount of model parallelism, and that enough amount of model parallelism is going to help us to be able to, fill up the computations across all the work. So the pipeline parallelism actually is a way for us to be able to make use of the model parallelism while gaining a bit more, overall reuse of resources, so that most workers are kept busy throughout this process. Okay, so this model parallelism was not being widely used before, but nowadays with the availability of bigger models, model parallelism is becoming more and more important. And most of the major frameworks you see specialized for training bigger models are going to have some form of model parallelisms and pipeline parallelism being built into their system. Okay, so I've talked about model parallelism, and let's come back and talk about another kind of parallel training. It's what we call a data parallel training. So in this particular case, the idea of data parallel training is you want to go ahead and look at the overall loss function of the stochastic gradient descent. And one thing you might notice is that we're going to try to take a mini batch, right? We want to be able to compute the gradient values on that particular mini batch. And in order to do that, one of the simple ways, you want to compute gradient values with respect to each of the input data points, and you sum those gradient values together. So in this case, of course, one of the simple way to do that, remember that a lot of those gradients for each of the instances is going to be computed independently. So what we can do is for a mini batch, we try to divide that mini batches onto a lot of smaller batches, and we're going to distribute that fraction of mini batch onto each worker. Within each worker, we're going to run the gradient computations in parallel, and then we're going to sum the gradient together. The good part of the data parallel training is that actually every worker runs the same replica. So there's no, effectively, there's no difference between the models that run on worker 0 and worker 1. The only difference is they're going to get a different subset of the fraction of a mini batch in here. Okay. So in order to run this data parallel training, there's one particular abstraction that's going to be quite useful. This abstraction called Allreduce. So the Allreduce is quite old API. It's actually an API that was being invented in the high performance computing community, and it's still going to be populated actually in machine learning community as well. So in this particular case, the way Allreduce works is that for each worker is going to have a local copy of an array in here. And then they can all go ahead and collectively call Allreduce. So after Allreduce, what's going to happen is that we're going to get a result array where each element is going to be the sum of the corresponding element across all the workers. So in this case, you can find that this 2 is the result of 1 plus 1, this 2 is the result of 2 plus 0, and this 4 is the result of 3 plus 1. Okay, So you can find that this Allreduce interface is kind of quite intuitive in some sense. So effectively, we are going to call Allreduce. Then you pass in an array, and you're going to get the sum of array across all the workers. Under the hood, the Allreduce can be implemented in different ways, and we don't have time to go through the way to implement Allreduce in this particular lecture. But if you are interested, there are other lectures. For example, I had a machine learning system lecture that talks about different ways to implement this particular Allreduce primitives across networks. There are a lot of the libraries that present this interface and implement it on different hardware. For example, NVIDIA have this library called NECO, NVIDIA Collective Library, that implements Allreduce along with other primitives. There are also other libraries like Horavolt, ByteDance PS, and so on that all implement a similar kind of interface in here. So how can we leverage this Allreduce interface to do data parallel training? The idea is that we're going to run different workers, right? So this is worker 0, and behind here there's worker 1 that runs exactly the same thing here, except that we're going to feed in a different set of data in here. So the only difference is the data, and each worker is going to run the same replica. Okay, so we're going to do is this: each worker is going to run the forward computation, the gradient computation. I'm going to obtain the gradient values throughout this process. And then all we need to do is we want to compute the sum of the gradient over all the replicas. Because if we get the sum of gradient, we'll be able to get that value and use that to run, say, stochastic gradient update in here. So all we need to do is to take G1, and I want to get big G equals G1 over all the replicas. You can find this exactly translating to Allreduce of G1 on this particular node. Right, so effectively, all you need to do is compute a gradient, run Allreduce, you get a big G1, and then each worker is going to apply the gradient update locally on them. And this is a simple way to implement data parallel training. One of the things you notice that in order to implement this kind of data parallel training, you don't need to change any lines of code in here. You just need to be able to directly take your input model, run it as is, but feed in a small fraction of data, get your gradient, and in your gradient optimizer, you are going to go ahead and do the Allreduce operations in here, and then do the gradient updates operation in here. So this is one way to implement data parallel training. There's another commonly used abstraction, which is called parameter server. So in this case, the idea of parameter server is that instead of doing Allreduce and get a gradient value and run the weight updates on each of the machines, we're going to run the gradient update or immediately after we get the sum of a gradient. And then the parameter server side, so there's a server side that's going to accumulate the gradient and run the updates and perform the weight updates on the server. So how can we use parameter server abstraction to do the data parallel training? Well, it's very similar to what Allreduce training is. So what we do is we will still run the same replicas across different workers in here. We're going to get gradient. The only difference is that instead of doing Allreduce and get sum of gradient value back, we're going to directly send a gradient value to the parameter server. After the parameter server get the gradient values, they will be able to do the sum of all the gradient values on the server side and run the weight updates there. Then it's going to send the weight back. So you can find that it's only a minor difference, right, between the Allreduce based data parallel training and parameter server based data parallel training. So what is the advantage of this parameter server style updates? One of the advantages is that in a lot of cases the parameter server don't have to wait until all the gradient to be available. Imagine that we have 100 workers in there, and one of the workers for some reason was slower than other workers. So in this particular case, what's going to happen is that this particular worker is this particular server, parameter server, is going to wait for, say, 99 gradient to arrive, but ignore the rest of the stale gradient. So in that case, it still gives you, you can still do the approximate gradient, right, by summing up the gradient from the 99 workers and do the weight updates. So the advantage of parameter server is that somehow, allows us to have a bit more robust training process if you want to have a more advanced strategy. And another advantage is that imagine that one of the worker dies and get restarted on another server node. All the worker have to do is to be able to pull the weights from a parameter server. So the parameter server kind of preserves a copy of a weight that allows us to be able to effectively, send to the corresponding worker when it restarts. So these are the advantage of parameter server-based implementation. There are quite a lot of parameter server implementations out there, such as ByteDance have a version called BytePS, and there are other variants parameter server implementation out there. Both the parameter server and Allreduce implementations, though, do have a common thing to pay attention to. This is how we can try to leverage the communication and computation and trying to let the communication overlap with the computation. So let us say, what do I mean? So let's imagine that I'm looking at the computation of a single worker in here. Right? You can find that one interesting thing is, as soon as we get the gradient value here, we want to be able to send the gradient value over to a network, either by Allreduce or parameter server, so that we can sync and update this weight. And then the weight will get back to each of the workers. We don't need to wait until the next iteration, until the next epoch, t+1. So one of the things you might find here is there are a lot of opportunities for these computation and communication to overlap. Specifically, when we are sending out the weights to a network doing Allreduce or parameter server-based synchronization, the particular computation of gradient calculation of later layers can still continue to happen. So it does not have to wait the weight synchronization to finish. We can still continue to run the corresponding gradient calculation there. And this computation and communication can happen in a concurrent fashion. Another interesting thing that you might notice is that we will get the gradient of later layers first because of the gradient calculation patterns. But we don't need the weight of later layers until the next iteration when we get to that forward point. Right? So what does that mean? That means that, actually, if there are already gradient and weights being communicated throughout a network concurrently, say that we're already getting to a point where we get the gradient of G1 in here, but we're still not yet finished sending all the G2s. In this particular case, maybe you want to prioritize the G1 a bit, right? Because we will need the weight 1 earlier than weight 2 at the t+1 epoch. So this is another thing that will be helpful for us to be able to prioritize, so that we can overlap the communication with computation, but also note that different weights and different gradients are being needed at different time point. We can leverage that property to allow us to get a better overall communication and computation patterns in this process. Of course, in order to implement this manually, there's quite a lot of complications because you kind of need to be able to have this two things running in parallel. But nevertheless, it is something that's really important for us to pay attention to. As a result, in most of the implementations, it's not as optimal if you just go ahead and do forward gradient computations, then do Allreduce, because in that case, your Allreduce does not overlap with your overall computation. A better way will be want to use what we call a synchronized Allreduce aggregation that immediately run Allreduce or immediately send the gradient to the overall networks as soon as you get the gradient value available. Okay, so this is kind of like a one careful trick that you want to consider when you go ahead and do system level implementations of this data parallel training. Okay, to sum up, today we have talked about different kind of parallel mechanisms. So we have talked about model parallel training that partitions up a computational graph and one thing to notice that in order for model paratraining to really be effective, you kind of need some form of pipeline parallelism here. We also talk about data parallel training that partitions the training workloads by subset of data, right? In all the cases, we want to be able to leverage opportunity to overlap the compute with communication so that you can get better overall computation, so that communication can happen with the computation, and you can hide the communication latency bar. It's the same case when you are trying to load the data from the disk or other cases onto GPU. That's the same thing. You also want to be able to hide the data copy from the outside to GPU concurrently with the GPU computation as well. Of course, there are other advanced parallelization techniques we don't have time to cover in this particular lecture. For example, Microsoft has a paper called Zero that tries to share the data across different machines. And there are also ways to automatically learn different ways of model and data parallelisms, and trying to automatically partition the workload so that this kind of parallelization can continue effectively. So here are some advanced readings you can go ahead and try and read. And but a lot of cases, the model and data parallelism are basic building element towards those more advanced methods. Okay, so that's the end of today's lecture. Hopefully you'll learn techniques of fitting bigger models onto your limited memory, as well as ways to scale up your computation. Thanks everybody for coming, and I'll see you in the next lecture.